Hi everyone. Today we will discuss Newton's third law of motion. So here if you see the statement, so the Newton's third law says to every action there is always opposed and equal reaction. Means that simultaneously, this means that simultaneously there will be action as well as reaction, and they are obviously when one is action another is reaction, so they are always opposed to each other and they will be same and equal in magnitude. Now this can also be narrated as mutual actions of two bodies upon each other are always directed to contrary parts. Contrary parts mean the other part. If object A and B are in contact, so if object A is applying force on B, that means B is the contrary part for this A. Similarly, object B applies force on A, it means A is the contrary parts for B. So here you can see every action there is always opposed and equal reaction, or the mutual actions of two bodies upon each other are always directed to contrary parts. Now let us elaborate this statement. So suppose two objects, let us say A as well as B, are in contact with each other. Now, so here this is the surface of contact or the point of contact. So A in that case will apply force on B and B will apply force on A, and this comes from the concept of the Newton's third law. Now force applied by A on B or force applied by B on A, they will be same in magnitude but opposite in direction. So that is the meaning of this statement or meaning of this statement. So force applied by A on B or force applied by B on A, they will be same in magnitude and opposite in direction. Now here you can see this representation. So here this is just a general representation that we have object A and B are in touch with each other. A is applying force on B. As soon as two objects are in contact, the third law is applicable only when two objects are in contact with each other. It cannot be used for a single object. It means there must be a pair of object or two objects, then only this third law will be applicable. So let us say A and B are two objects which are in contact with each other. Here just to represent this direction we have separated them. Okay, so now A is applying force on B and B is applying force on A. So this representation you can see A is applying force on B and B is applying force on A. So F of BA, when we say F of BA, means A is applying force on B. Force applied on B by A. When we say F of BA, means force applied on B by A. Similarly, when we say this F of AB, so force applied on A by B. So we have this F of BA as well as you have this F of AB. Now here we can say from the Newton's third law, and these two forces they will be same in magnitude but opposite in direction. So we can write F of BA, it is equal to minus of F of AB. So if you write it in terms of equation, so we can write F of BA it is equal to minus of F of AB. So that you can see in this. So here if you again see whatever we have discussed or whatever we have narrated. So the first and second laws are a statement about a single object. It means whether you have the Newton's first law or Newton's second law, they can be considered for a single object. But the Newton's third law, it is always for pair of object, because here there has to be force of action and reaction. And when there is force of action and reaction, that will be possible when two objects are in contact with each other or two objects are applying force on each other. So to discuss the third law, we require two subscripts for the force. When we say subscripts, just now we have used, whether we have used F of AB or we have used this F of BA. So these are your subscript. Force applied by A on B, force applied by B on A. Either you can say like this, or you can also read it like this. If you write this as F of BA, force on B by A. here we can write f of AB if we write force on A by B. So all these are the nomenclature, the narration, and that way we can always pronounce this. Now here, as we have just discussed, f of AB, it is equal to minus of f of BA, because f of AB, if it is acting in the leftward direction, then f of BA, it is acting in the rightward direction, because both the forces are equal in magnitude but opposite in direction. So opposite in direction, so if you treat this as positive, then this will be considered as negative. So they are same, it means this equal to this but with the negative sign because the directions are different. So we say f of AB, it is equal to minus of f of BA. Now here from this equation, if you consider this, these are the narrations that we have just discussed, that you can see. Two forces are often called action and reaction pair. So one force, if it is supposed as active force, another will be termed as the reactive force. So from there we get the concept of action as well as reaction. One of the forces is called the force of action or simply action force, and the other is called the force of reaction or simply the reaction force. Which force is called the action and which force will be called reaction, that depends on us. We can name this force as the force of action, then this force can be represented as force of reaction or vice versa. If you say this is the force of action, then this will be termed as the force of reaction. So that depends on how we pronounce, how we feel, which will be termed as action, which will be termed as the reaction. There is no parameter used for this, and we are free to use any force as force of action, then the other will be termed as the force of reaction. Now if you consider this Newton's third law and the Newton's second law, from these two laws, if you combine these two laws or if we study these two laws together, we get a new concept, and that is termed as the law of conservation of momentum. So considering the Newton's second law as well as the third law, we get the concept of the conservation of momentum. Now you can see how we get the conservation of momentum. So suppose we have these two masses in contact with each other, let us say m1 and m2. This is mass A and this is mass, suppose B, if you name it as A as well as this B. Now obviously m1 is applying force on m2 or m2 is applying force on m1, or object A is applying force on B, object B is applying force on A. So we have seen that f of AB, in that case it will be equal to f minus of f of BA. Now using this relation f of AB, it is equal to minus of, suppose, f of BA. Now suppose this system is moving with some velocity v. The entire system is moving with the velocity v. It means the momentum carried by this object will be how much? m1v. Momentum carried by this object, it will be m2v, because momentum is defined as mass into velocity. So m1v as well as m2v. So suppose at some particular time it is moving with the velocity u. Its initial velocity is u. So momentum carried by this, it will be m1u. Momentum carried by this, it will be m2u. After some time, suppose their velocity becomes v. So it will be m1v and m2v. So change in momentum. So change in momentum for this, it will be how much? m1v minus m1u. This will be for the object A. Similarly for object B, it will be m2v minus m2u. Now this change, so suppose we call this as change in momentum, let us say delta p1, and this as change in momentum delta p2. Now let us say this momentum change has taken place in some time interval delta t, okay, or this delta t. So delta p1 upon delta t, this change has happened in this time interval delta t, or this change has happened in time interval delta t. So rate of change of this momentum, it will be how much? Delta p1 upon delta t. Similarly, delta P2 upon this delta T. I hope this is clear. So this gives you the rate of change of momentum. Now the same thing if we write in the differentiated form, we can write this as so this is your object A and this is object B. For this, the change in momentum we have considered, and rate of change of momentum delta P1 upon delta T, and for this we have considered delta P2 upon delta T. Now the same thing if we consider for the in the differentiated form, considering for the very small time interval, then we can write this as dP1 upon this dt, and for this you can write dP2 upon this dt. So this is the rate of change of momentum for object A, and this is rate of change of momentum for object B. Now considering the Newton's third law, we have f of AB, it is equal to minus of f of BA. F of AB, it is equal to minus of f of BA. Now f of AB, this is the force experienced by this object, and similarly f of BA, this will be force experienced by this object, or either way we can change the nomenclature. So force experienced by this object, if we say it is f of AB, then can we replace this by dP1 upon dt, because from Newton's second law, this statement we get from Newton's third law, and from second law we get rate of change of momentum, it is equal to force F. So rate of change of momentum, here it is dP1 upon dt. So we can write dP1 upon this dt, it is equal to minus of dP2 upon this dt. So dP1 upon dt is minus of dP2 upon dt. This clear? So this we get from Newton's third law. This we are getting replacing force as rate of change of momentum we get from the Newton's second law, and we have used this relation. Now see here, f of AB is equal to minus of f of BA. So from here we get another concept. If you write f of AB plus f of BA, it is equal to how much? 0. If you bring it to this side, so f of AB plus f of BA, it is equal to 0. F of AB is what? Force applied by this object on this object, or f of BA is force applied by this object on this. When we say force applied by this object on this, it means it is an external force. Force applied by one object on the another object, it means it is external force. So here this object is applying force on this, it means that is external. This force is applying force on this, that is also external. Now if we consider this equation and if we simplify, we get f of AB plus f of BA, it is equal to 0. It means the net external force, or the summation of all external force acting on the system, it is equal to how much? 0. F of AB plus f of BA, it is equal to 0. So summation of all external forces, because here these are the only two external forces, and sum of these two external forces, it is coming as 0. So summation of all external forces acting on the system, it is equal to 0. I should put this vector notation here so that you can consider all this, because momentum is a vector quantity and force is also a vector quantity. If you want, you can, wherever we have force, you can put that vector notation. So summation of all external forces, it is equal to 0. So that is the prerequisite, that is the required condition. That is the required condition for the conservation of momentum. So now let us come back to this statement. So again here, can you write this dP1 So we have concluded that summation of all external force, it is equal to 0. Now under this condition, we are observing dP1 upon this dt plus dP2 upon dt, it is equal to 0. Now this is first order differentiation of P1 with respect to time t. This is first order differentiation of P2 with respect to time t, using the concept of the differentiation, we can realize as this is differentiation of P1 plus P2 with respect to this time t. And d of P1 plus P2 divided with respect to t, that is 0. Now, you know, differentiation of first order differentiation of only constant term is 0. So, differentiation of P1 plus P2 as a whole with respect to time t, it is equal to 0. It means differentiation, and we know from the concept of this differentiation that the first order differentiation of only constant term is 0. That is only possibility. So, from this can you conclude that P1 plus P2 it is a constant quantity. So, sum of the momentum it is always constant. Constant means it is always conserved. So, summation of momentum it is a conserved quantity. So, from this we get this statement, and this gives you the law of conservation of momentum. It means if summation of all external force if it is suppose 0, then momentum always remain conserved. There will be no destruction. It is always it can change its nature, but the total momentum of the system it will always remain constant, or it will always remain conserved. So, this we get from the combining the Newton's second law as well as third law. So, we have this relation. Now, whenever you use this condition that sum of momentum of a system is always conserved, it means you have to check back the condition that summation of all external force, this one, summation of all external force acting on the system, it has to be 0. If there is the presence of external force and summation or the resultant of external force if it is not 0, in that case you can't use this concept. We will be able to use this concept only this condition is justified or it is satisfied. So, this we are getting from the Newton's second law as well as third law. When we combine and when we observe these two laws together, so we get the third law or third concept you can say, and that gives you sum of momentum it is conserved. This you can also represent like this: summation of momentum of a system it is always conserved. So, summation of momentum is constant. So, we will discuss problems based on Newton's first law, second law, third law in the coming classes. Thank you.